What's up, everybody? This is EchoLynx. Today, we're going over the Extending Your Network Room from TryHackMe. We'll get started with Task 1, Introduction to Port Forwarding. They give you two examples here. It's just an introduction, so we don't have to go into great detail. Let's say this web server is hosting a website on port 80. In this first diagram, only the two other computers on the same network can reach it because it's hosted inside the local network, an intranet. Port forwarding lets you take that internal service and make it reachable from the internet. In practice, you configure the router to forward external port 80 on the public IP to the internal web server on port 80. For example, forward 82.62.51.70:80 to 192.168.1.10:80. Now, when someone connects to the public IP on port 80, the router forwards that traffic to the web server. Responses flow back automatically as part of the same connection. It's easy to confuse port forwarding with a firewall. Port forwarding opens a specific port so traffic can be forwarded inward, while a firewall separately decides whether that traffic is allowed across those ports, even if they're open. Question: what is the name of the device that is used to configure port forwarding? Answer: router. Task number 2 is Firewalls 101. A firewall is the border security for your network. It decides what traffic is allowed to enter and what's allowed to leave. And it does that by inspecting packets and checking things like where the traffic is coming from, where it's going, which port it targets, and which protocol it's using. In practice, you'll see firewalls as dedicated hardware in bigger environments, built into residential routers at home, or even as software like Snort. However they're deployed, the job is the same: inspect traffic and apply the rules the admin has set to permit or deny it. There are two primary categories we care about here. A stateless firewall looks at individual packets against a static rule set. If a packet matches an allow rule, it passes. If it violates a rule, it's dropped. It doesn't track the bigger conversation, which makes it lighter on resources, but only as smart as the exact rules you write. That simplicity can be useful when dealing with huge volumes from many hosts, like during a DDS. A stateful firewall, on the other hand, pays attention to the entire connection. It uses the full context rather than a single packet to decide what to do, so its decisions are dynamic. That power costs more resources, and you can see behaviors like allowing early parts of a TCP handshake that later get blocked when the overall connection looks bad. If a host's connection is deemed malicious, a stateful firewall can block the whole device, not just one packet. For the quick questions at the end, for this room, the OSI layers are 3 and 4. The category that inspects the entire connection is stateful. The category that inspects individual packets is stateless. Task number 3 is a practical firewall. Click View Site to launch the static lab. You'll see traffic flowing toward the web server at 203.0.110.1. The packets marked red are malicious. The green ones are legitimate. Your goal is to keep the malicious traffic from reaching the server. In this challenge, the thing you must block is port 80 traffic to the web server. Configure a rule that denies, drops any packets whose destination IP is 203.0.110.1 and destination port is 80. If the UI asks for protocol, choosing TCP or any will both satisfy the intent since the lab's target is port 80, HTTP. You don't need to single out the attacker's source, just block inbound traffic headed to 203.0.110.1:80 so the red packets stop at the firewall while green, non-matching traffic continues. Once the rule is active, watch the red packets get blocked, and the site will display a flag. Copy it exactly and paste it into the answer box in the brace format shown in the prompt. Submit the flag and you're done with task number 3. Task number 4 is VPN basics. A VPN, a virtual private network, lets devices on separate networks talk securely by creating a dedicated path over the internet called a tunnel. Think of it as a private lane carved through the public roads. In the room's diagram, you've got network number 1. office number 1, and network number 2, office number 2. When two devices establish a VPN, they also form network number 3, the tunnel. Those devices are still part of their original networks, but they also share this private overlay where only tunnel-joined devices can communicate. Why bother? First, VPNs connect sites in different locations so teams can reach internal resources from another office. Second, they provide privacy. Traffic inside the tunnel is encrypted end-to-end, so only the sender and intended receiver can understand it. Useful on untrusted public Wi-Fi, where the network itself offers no protection. There's also an anonymity angle. VPNs can hide your traffic from intermediaries like ISPs, though the real privacy you get depends on how the VPN provider handles logs. In our context, TryHackMe uses a VPN, so you can securely interact with vulnerable machines without exposing them to the whole internet. And so your ISP doesn't think you're randomly attacking hosts online. The room also walks through common VPN technologies. PPP is the building block used by PPTP. It handles authentication and encrypts data using a key/certificate pair that must match. But PPP on its own isn't routable. It can't leave the local network by itself. PPTP is the tunneling method that carries PPP traffic across networks. It's simple and widely supported, but its encryption is weaker than modern options. IPSec uses the existing IP framework to encrypt and protect traffic. It can be trickier to configure, but it offers strong encryption and broad device support. For the quick questions at the end, the VPN technology that only encrypts and provides authentication, not routable by itself, is PPP, and the VPN technology that uses the IP framework is IPSec. Task number 5 is LAN networking devices. A router connects networks and passes data between them. That process is called routing. Routers operate at layer 3 of the OSI model and pick a path across networks, so data gets delivered successfully. In real environments, there can be multiple possible paths between two networks, and different routing protocols choose the best route based on things like shortest path, reliability, or even the speed of the link, copper versus fiber. Routers are dedicated devices and don't perform the same job as switches. They also usually give admins an interface, web page or console to configure features like port forwarding or firewall rules. A switch is a dedicated device that lets many machines on the same network talk over Ethernet. Switches can operate at layer 2 or layer 3, but a layer 2 switch does not operate at layer 3. A layer 2 switch forwards frames to the right device using its MAC address table. Its entire job is moving frames to the correct port on the local segment. A layer 3 switch is more sophisticated. It still switches frames like L2, but it can also route packets using IP, similar to a router. In the room's example, you'll see a layer 3 switch with interfaces like 192.168.1.1 and 192.168.2.1. That's inter-VLAN or inter-subnet routing happening on the switch itself. This ties into VLANs, which virtually split devices into separate groups even though they share the same physical switch. VLANs let you keep departments like sales and accounting isolated, so they can both reach shared resources like the internet, but not freely talk to each other, unless you explicitly allow it. That segmentation improves organization and security by limiting how devices communicate across groups. For the quick questions, the verb for what a router does is routing. The two layers of switches are layer 2, layer 3. Task number 6 is the practical network simulator. Click View Site, use Chrome or Firefox as the room suggests, then send a TCP packet from computer 1 to computer 3. Type a simple message like, "Hello," hit send, and watch the simulator break down every step from point A to point B. When the TCP exchange completes, the site will reveal a flag. Copy it exactly and paste it into the answer box in the brace format shown. Open the network log and count the entries labeled handshake. That number is your second answer. in this case, will be 5. Submit the flag and the count, and you're done with task number 6. With this, the module network fundamentals are finished. Next will be how the web works and starting with DNS in detail. I see you there.